Hello. I hope you're doing very well and you are going to be prepared for your next quiz, which is quiz number 3. Okay, I'll post a practice quiz for you, a practice quiz, maybe tonight. And then the list of the assignments is going to be due on the quiz number 3. As usual, it's going to be a take-home quiz. You just do the quiz and go back to the quick courses and you submit it. So what we would like to do is we'd like to finish the chapter 4 that I talked about that linear transformation the other day from the preliminaries from 1.8, the definitions. So I'm going to continue. There are a couple of property of linear transformations that we're going to be interested in, mostly in 4.10. Okay, so I'm going to discuss about that one. Some special linear transformations given to you in 4.9. If you like geometry, you can read it for yourself. We are not going to use it for the rest of the course. Okay, so we focus on the property in section 4.10. So this is where we are going to give you the quiz. So I'm going to try to give you a summary of the leftover after the transformation. Remember, we talked about the other day, we introduced a special linear transformation is just a function. It's a function between two vector spaces. But it's not ordinary function like in calculus. It got some other extra properties. The extra properties is the function, we call it the transformation. It must transform the property of one vector space to the other one. The property of the vector spaces are they are closed and they are vector addition and scalar multiplication. So if the function would carry these two properties from one vector space to the other one, this is our function that we call it linear transformation. Okay, just go back to my notebook and to see what was the leftover from the other day. We make sure we get everything related to the definition of a linear transformation, and we give it a new part. Okay, so this is what we end up the other day. So the idea was we want to change this linear transformation from a function format into the matrix format. Okay, so we introduce a great theorem for you. You see, that was the idea. The idea is if you give me a matrix, you see this is the way we started. So if you give me a matrix, okay, if you give me a matrix A, quickly I can form a linear transformation for you. So this is it. I define the matrix as n by n. So I define a transformation from Rn to Rm by this definition, A times X. A is the given matrix and X is the variable. And I prove that this is going to be always a linear transformation. So this will tell you that we can form many linear transformation. Okay. So the question was, if a linear transformation in general is given to you, can you write it down in this form? Can you find a matrix so that this, okay, this matrix would be associated to your linear transformation? We investigate one example and we find out, yes, it's possible. It's possible because we can look at this as just a kind of system of 3 equations, 3 variables with this equation, and we just pull out the coefficient of the, okay, the matrix of a coefficients. And when we organize it, we find out, oh, we get the A here. So a linear transformation can be written as a linear transformation introduced by a matrix. Then we find out that we can give you a general theorem. That was a great theorem that if you give me a linear transformation, I can form a matrix for you. What's going to be the column of those matrices? So this is a finite dimensional space. It would have the standard basis, E1, E2 to En. So what we did, we evaluate the function at E1, E2, E3 to the En, and we get some column vectors. We put these columns together, and we claim that that is a matrix in question. Okay, so this is quickly to find out a matrix. We call it the standard matrix, corresponds to the given, okay, a given transformation. And we give you the proof of this one. So we end up with example. Okay, this is it. And this is a linear transformation, like a function of several, 3 variables in calculus 3. So if you want to find officially using this theorem to find the matrix, the column of a matrix is T of E1, E2, E3. So evaluate the function at these 3 vectors, and then you put this as a column. So that gives you the matrix A associated to your linear transformation. Talk about the shortcut. Just think about it as a system of the equation, and we just write a coefficient matrix if you like. Okay, this is 3 variables, x, y, z. So this is the matrix of a coefficient, and quickly we get the A. Okay, so I'll give you a couple of more examples of how we're going to find the standard matrix. So that was the first part, finding the standard matrix. So basically, when you got this one, this means T is equal to the, okay, T is equal to the TA if you like. And the A is the one that you find. Okay, so that was example number 1. Let's try a couple of more of these examples. So we continue. So this is the second one. You'll be given T of x1, comma x2, comma x3, 3 variables, is equal to, okay, is equal to the x1 minus 2x2, okay, plus 5x3. That's the first component, and the second component is it's a 2x1. When I post your practice quiz, you see quite a lot of these, and even if your assignment, 3x2, and the last one is 4x1 plus x2 minus 2x3. Okay, this is going to be a function. As you can see, this function t is from R3 to R3. So your matrix is going to be, you see the solution is that this t is going to be a function from R3 to R3. So A is going to be, A is a 3 by 3 matrix. So A is a 3 by 3 matrix. Okay, and you can find it quickly. This is going to be A equal to, okay, a 3 by 3. So look at these. The quick one is just guess the matrix of a coefficients. 1, 2 is going to be 1, -2, 5. Okay, this is going to be a column of that. You see the column would represent the x1, x2, and x3. So over here it's going to be 2. There is no x3, so it's going to be 0. And over here it's going to be 4. Okay, it's going to be 4, 1, and -2. So that's a short form. Otherwise, you have to find the T of E1, T of E2, E3, and you put them together. But we would like to get this one right away. Okay, so it's a matrix of a coefficient. If you think about this one as a column vector, and those each of these is going to be an equation in your okay, in your system. So this is it. Your T is equal to the TA, if you like. Okay, you know that TA of x is a times x. Okay, so that's a number 2. Let's have another one, number 3. Okay, the number 3 is this is a given transformation. Transformation is T of x1, comma x2, x3, and x4. And this is given as, okay, this is it. It's given at, I have the x2 minus 3x3. And then I have 2x1. Okay, it's going to be 2x1 minus x2 plus 3x4. Okay, and comma. and I have the other one is 8x1 minus 4x2, sorry about that, I have to go down, plus 3x3 minus x4. Okay, so the last one is 8x1 minus 4x2 plus 3x3 minus x4. This is going to be your linear transformation. So solution, you check to see that the t, okay, what is going to be t? T is going to be a function from 1, 2, 3, 4, from R4, okay, from R4 to the 1, 2, 3, which is going to be to the R3. Okay, this is going to be R3. Remember, this is going to be when it is given to you. So your matrix is going to be a 3 by 4 matrix. Okay, so this is going to be from R4 to R3. Is always, remember, this Rm to the R. Okay, this is it. It's going to be Rm to the Rn, and the matrix is going to be, so A is a 3 by 4 matrix. Okay, because when you write this one as a system of the equation, you have 4 variables. So 4 variables means you have to have 4 columns. See, 1, 2, 3, 4, and this is going to be your columns. Okay, so this is going to be the matrix. The matrix A is going to be equal to, see the first one. Remember, you have 4 variables. There is no x1, so this is going to be 0. Okay, there is no x2 over here. That's x2, so it's going to be 2. x3 is equal to x3, and the x4 is 0. Okay, so it's a kind of, x1, x2, x3, and x4, your variables. Okay, and the second part is going to be 2, -1, 2, -1, there is no x3, and the x4 is 3. Okay, and the next row is going to be 8x1, 8x1 minus 4x2, 4x2, and then the 3x3 and minus x4, which is going to be a negative 1. Okay, so this is going to be matrix A. Is a matrix A, and then you can see that this is it. The T is equal to the TA. So this means if you want to find the T of X, it simply is going to be A times X. When A is this one, and your X is X1, X2, X3, and X4. Okay, so be quick, because in the problems that you are going to have, you should be able to find, okay, you should be able to find these matrices for us to get the numbers. Okay, so this is that's very nice, because this means you have only one type of linear transformation. You have the one that associated with the matrix, because if you give me any, I can change it for you. Okay, so that would be very much an advantage to work with this type of functions. Okay, now what we're going to be interested in, since you got this kind of a one-to-one correspondence, if you like, between linear transformation and these matrices, then you can look into the different property of these transformations. Okay, so what we are going to do, basically, we are interested in the case that, as you can see, t is a function. You know that the function can be one-to-one, or the function can be invertible, and we can find the inverse of a function. Because the inverse of a function of one variable is easy to find, right? If somebody give you this one, and they ask you to find the inverse of this function, it's not easy. So the question is going to be, if a linear transformation is given to you, and you're sure that this linear transformation is invertible, what is the inverse of this? So what we're going to do is we are going to connect it. You see, this is it, the connection. We are going to show that T would be invertible even only if A is invertible. And nicely we can find the, okay, so what we expect is that the T inverse would be equal to the A inverse of X, and to be able to find it. So this is what we're going to do. And this is what you have in section 4.4.10. To talk about invertibility, first we need to talk about the composition of two functions, composition of two transformations. Okay, so that's the idea. Quite nice. It seems to be clear or obvious, but you have to prove it. Okay, so this is it. That's the idea of 4.10. It's not bad, not complicated section. 4.10, 4.9, some special transformation like the reflection, okay, shifting, etc. If you get time, we talk about it, but we don't need it. You can read it yourself. Okay, so what is 410? We want to know what's the composition of two linear transformation. Composition, okay, composition of linear transformation. Linear transformation. You are familiar with the composition of two functions. Okay, so we are going to use the same idea, but we are going to make it easy formula to apply, okay, because everything would depend on this associated transformation, okay, we associate it with the matrix. Okay, so what we're going to do, we are going to define it. Suppose now you know that each linear transformation can be defined by a matrix. So we're going to consider those special one only. Suppose that T sub A is going to be linear transformation from Rn to Rk. Okay, that's one. And another transformation, we call it T sub B. So A is associated matrix with the T, and this is the associated matrix for the second one. And this is going to be a function defined from Rk to the Rm. You know that the domain and the range of the one in between must be the same. If they are going to be given, okay, are given linear transformation, linear transformation. If they are linear transformation, then we can define the composition. Then the composition, okay, the composition of a TA and a TB is going to be denoted by, we can have two, but I'm going to define this one, be denoted by TB O TA. So it's a composition of TB and the TA. Okay, and this is going to be what? You got to be careful. Okay, so what's going to be the domain and the range of this? We apply the TA first, so we start with the Rn. We start with the Rn, okay? So TA would take us to the Rk, and then we start with the TB, which is from Rk to the Rm. So this is going to be a linear transformation between, okay, between Rn and Rm, like the one that you do with the function. Okay, so the composition of two functions. Okay, the inside function is TA, so you apply the TA first from Rn to Rk, and then when you're done, you just continue. That take you to the Rm. So it's going to be denoted by this and defined by, and is defined by So the definition is like the definition of composition function. So TBOTA, okay, if you want to find it at X, remember the inside function first, it's going to be outside function TB of TA, okay, TA of X, TA of X, and this is going to be true for, okay, for all vector X, X in Rn. Okay, so this is how we define the composition of okay, of two linear transformation. Okay, they call it product, but it's not the product, it's a composition, if you like. Okay, so the thing that we can prove is going to be, because this is in calculus, you're done. But this is linear algebra, so we want to show that these two are linear transformation. The result is so far a function, but we are going to prove that this is also a linear transformation. Okay, so we prove that this is going to be linear. Okay, so this is going to be one. So you note that. I have to prove it. It's note that our claim is this new transfer function, if you like. It's a linear transformation. Is linear. Is linear, you have to prove it for us. So what do you mean by linear? So you mean that if you operate on the vector addition, okay, if you have two vectors, T of x1 plus x2, you can distribute it. So apply the definition first. So the definition is going to be TB of TA of x1 plus x2. Okay, that's your first step. But you know that TA is linear. It's a linear transformation. So this is going to be equal to the TB. You distribute this one, so that gives you TA of x1 plus TA of x2. Okay, of x2, because this is going to be linear. Okay, so now we continue. So this is because TA is linear. Okay, but TB is also linear. So TB would transfer the addition to addition. So this is going to be TB of TA of x1 plus TB of TA of x2. The reason, because TB is linear. Okay, if you use the definition that we talk about it, this would be simply what? This simply would be TB or TA at x1, and this would mean TB or TA at x2. And that's exactly means TA is going to be linear, okay? So that's the first step. So we prove that TB of AX1 plus, okay? So this is it, I rewrite it. We prove that TB or TA of x1 plus x2 is simply TB or TA at x1 plus TB or TA at x2. Okay, that's the first property of the being linear. The other property, so we just carry the addition to the addition. The other thing is the scalar multiplication. Okay, what's the scalar multiplication? That's easy. A TB or TA at alpha. Okay, let's say alpha x1 or just alpha x. You want to prove that you can bring out the alpha. So use the definition. It's going to be TB of the TA of alpha x. But TA is linear, so it means you can bring the alpha out. So that give alpha. times TA of x, but TB is linear, so we can bring the alpha out. Alpha out of TB, okay, TA of x, and that's exactly alpha TB or TA at x. Okay, so we proved the two-stroke property. So the composition of a TB and the TA is linear. Okay, so the composition of two linear transformation is a linear transformation. Okay, so you have to know. Now you know it, but you have to, a little bit, give us a little bit proof and to show that this is going to be true. Okay, now we can make it easier to handle because these are familiar. You see, I just directly use the linear transformation associated with the matrix because this is the way we do it. Now, let's see if we can bring an easier formula, because since it's a linear, you should be associated with the matrix. So this is how we associate with the matrix. Okay. So there you are. Since it's a linear, you say, oh, I have something extra for you. Note that. Okay, that something extra is what? We note that the T of A of X is simply A times X. Okay, this is going to be the case. So if you want to compose TB or TAX, if you use the definition, it's going to be TB of TA of X. But according to this argument, you can replace this one by AX. So it's going to be TB of AX. But how about definition of the TB? Remember the definition of the TB is what? Is going to be B times the vector times A times X. Okay, and we can write it down as, we can write it as a BA times X. So we get something that we expected. So this means okay, when we compose them together, that linear transformation is going to be again linear transformation associated with the matrix. What is the matrix? There you are. If you compose the TB and the TA, okay, TB and the TA at X, it is easily equal to B times A times X, you see? So the composition of two linear transformation corresponds to the multiplication of their corresponding matrices. Okay, because this is the associated matrix is B, associated matrix is A. So instead of writing formula in that format, this is it. We can write it down quickly and get those numbers. And that's why when we talk about the multiplication in, okay, at this time, if you like, directly we say multiply if somebody say we want to multiply linear transformation, simply compose them, but it's a kind of multiplication because you multiply the corresponding matrices, okay? So this is your job, you must know it. So two linear transformations would be given and they ask you to find the compositions. So you can use this formula. So your job is you have to find the A, you have to find the B, then you multiply them together and that give it the result. Okay, you have quite a lot of problems on your on your assignment, and we give you one of them. Okay, so the conclusion is you compose two linear transformation, you get the linear transformation. Now, do you have a formula for it? Yes, this is the formula for it. Okay, so your job, there you are. Two linear transformation would be given, and they ask for their composition. Suppose, there you are. Suppose the T1 and the T2. T1 and T2 are linear transformation, are linear transformation. Okay, linear transformations from, okay, they are from R3 to R3. R3 into R3, such that the definition, this is going to be the definition. T1, okay, T1 at X, Y, Z is equal to the 2X plus Y 0 and X plus Z. That's a T1. T2, T2 of X, Y, Z is equal to the X minus Y, comma, Z, comma, Y. Okay, so this is two linear transformations. So what they want you to find, you know that you are going to find this standard, this would have a standard matrix A1, A2, then you can compose them together. They ask you to find the standard matrices, the standard matrices for these compositions. The compositions T2, OT1, and T1, OT2. Okay, and then the formula. Express also, if you like, or then just would like you to express T2, OT1 and T1, OT2 in terms of formulas, in terms of X, Y, and Z. Because we like the formula, algebraic format, not the, okay, not the matrix format. Okay, basically we want to find it. This is a T1 and T2. So what's the composition of these two? Okay, this would be very useful to function of several variables. It's not easy if you want to do it directly. Okay, now you know the formula. So what you're going to do is, this is the formula that we talk about it. You see, if you compose them together, their corresponding matrix is going to be B times A. So you have to find the B times A, then with this, that give you the formula, okay? So you are going to find the matrices corresponds to the T1 and the T2, okay? So this is going to be your solution. You are going to find, okay, you are going to, this is it. Say that the note that, let's call A1 is going to be the matrix corresponds to the T1. Talk about the shortcut that we have. It's going to be 3 by 3 matrix. These are like the system of the equations. So yeah, there is going to be 2, the coefficient of the X, coefficient of the Y. There is no Z, so that's going to be 0. The second one is all 0, so it's going to be 0, 0, 0. Okay, and the last one is going to be X plus C. X plus C, the coefficient of X is 1. There is no Y here, and the Z is 1. So this is going to be a matrix correspond to the T1. Okay, then we get the A2. A2, this is it. And for the A2, it's going to be a 3 by 3. The first row, that give you 1. The coefficient of the Y is a -1. There is no Z. The second one is Z, so there is no X and no Y, but Z. The last one is Y. There is no X. Okay, this is it. There is no X, but 1 Y, no Z. So that give you the A1 and the, okay, the A1 and the A2. Okay, now you know that according to this formula, you have to find their product. Okay, find the product of the A2 times A1, and then that give you T2 or T1. Okay, so just remind you that the T2 or T1, okay, if this is going to be the case at a number, okay, uh, this would correspond to the, you call it the X, it would be correspond to the A2 times A1, if you like X, okay. So we are going to find the A2, A1, so multiplying together. So what is going to be A2, A1? A2 times A1 is going to be A1, the matrix is a 3 by 3, it's a 1, negative 1, 0. The second one, 0, 0, 1. Okay, 0, 1, 0. Multiplied by A1. The A1 was 2, 1, 0. 2, 1, 0, 0, 0, 0. And then we get the 0, 1, 0. Okay, so that's going to be the one. Now multiply together. It's easy to multiply. You know that the row column you multiply. If you multiply this one, that give you only 2. Okay, you multiply, go forward, and over here we get a 1, 1, 0, and you do the rest. And this would be the answer, 1, 0, 1. And the last row would be 0, 0, 0, because if you multiply, that give you 0. This is 0 and the 0. So this is going to be a situation we're going to have. Okay, so it's going to be A2 or T1. Now we are ready to give you the T2. So if you want to write the formula, T2 or T1 at x, y, z, x, y, z is going to be equal to, just change this one into those system of the equations if you like. Remember, this is going to be x, and this is going to be y, and this is z. So this first one would be 2x plus y. That's the first one. The second one would be x, and there is no y, plus z. And the last one is all 0. So that's the formula for the composition of T2 or T1. See, very nice and easy to find. So just find the corresponding matrices. The product of a matrices corresponds to the composition. So if you want to do the other one, you have to find the A1, A2 first. So it's going to be A1, A2. Okay, so you multiply these together. So that gives you 2, 1, 0, 0, 0, 0. And that's a 0, 1, 0. And then you're going to multiply by the 1, negative 1, 0. And this is going to be 0, 0, 1. And we have the 0, 1, 0. Okay, multiply this. If you multiply it, you see if you multiply this one, that gives you 2. If you go forward and you do the other one, that gives you a negative 2. If you multiply this one by the third column, that gives you 1. If you do the second one, everything would be 0. And if you do this one, that gives you see, if you multiply, that's, I think I missed something. This is 210. I'm sorry, this must be the A2. Let me just check the A2 again. So for that was 101. Okay, 101. and 0, 1, 0. Switch, just switch it. Okay, I missed something that is going to be, so that was the one. Yes, that's A2, A1. It's A2, A1. So this is the A2 and the A1. For the A1, sorry, this is 1, 0, 1. 1, 0, 1. Because the A1 is 1, 0, 1, but you get the same thing here. Okay. This is going to be the case. So if we check the last one is 0 is correct. So here again, this is 1, 0, 1. 1, 0, 1. Okay, 1, 0, 1. And the other one's going to be 0, 1. Okay. So this is going to be the case. So I check this last one to make sure that I get it all right. Okay, so if you multiply this one, you see if you multiply by this, so that give you a 1 here. And if you multiply by the second one, that give you a -1 and a +1 that make it into 0. If you multiply by the third one, row column, everything would be 0. So that's going to be the case. Okay, so that's going to be A1, A2. Now we are in a position to give you T1. So what's going to be T1 or T2 at X? Okay, at X, Y, Z. Okay, at X, Y, Z, and there you are. So this is X, this is Y, this is Z. So the first component is going to be 2x minus 2y plus z. That's the first one, comma. The second one, everything is 0. And the third one, you get only x. So this is going to be the composition of these two linear transformation. Okay, this is the way we operate with these new functions, if you like. Okay, so as you can see, that's changed things quite a lot and make it much easier to handle this type of function. Okay, so this is going to be a linear transformation. So remember, our target is invertibility. So we want to know how we're going to find the inverse of a linear transformation. A function of one variable is easy. You know that you have something like y equal to the 3x plus 1. You solve for x, you get the inverse. But it's not going to be easy for this, okay? But if you change it into the matrix form, that would be easier to handle. So the idea is when we want to talk about the inverse function, you know that you have to have the square matrix, okay, matrices. So it's not going to be n by n. So we're going to consider n by n matrix. The corresponding transformation is called operator. So basically you want to find what is the inverse. What is the inverse of a matrix operator? So operator is a linear transformation from one vector space to itself. If you have vector space V, any transformation from V to V, they usually refer to it as an operator. Okay, so this is going to be the case. Suppose A is, it must be square, is an n by n matrix. Now the corresponding operator, and TA from Rn to Rn, okay, is a given operator. So we call it operator because it's a linear transformation from a vector space to itself. Or you can call it linear transformation if you like. You see, or a linear transformation. But when the imagine the domain is going to be the same, we call it an operator. Okay, now we want to define the inverse. Okay, you know that for the inverse, the function must be a one-to-one. So we have to define the one-to-one. Okay, if this is going to be the case, then TA. Okay, TA is set to be. Okay, set to be one-to-one, like a function. Okay, if it's going to be one-to-one if for each two vectors, each vectors u and v in Rn, okay, Rn, this is going to be the case that if Tu is equal to the Tv, then u must be equal to v. It's the same thing that we do for the algebraic function. We call it horizontal line test. Every horizontal line intersect the graph of the function at one point only, then the function is going to be one-to-one. Okay, or this is equivalent to say that if u is not equal to the v, then t of u is not equal to the t of v. So different points goes to different numbers in the domain, in the range of the function. So if this has happened, we say the function is going to be one-to-one. Okay, it's very easy to prove that this TA is one-to-one if and only if this matrix A is invertible. So invertibility of the A, of the transformation T, and the invertibility of the matrix A coincide. That's natural because you know that they are associated to each other. And so it's not difficult to prove. I'll just give you an idea. Note that that's crucial for us, you know, for the argument that we're going to have. Note that this is going to be a T of A. You know that the formula is A times X is going to be one-to-one, is one-to-one, even only if the matrix A is going to be invertible. A is invertible. Okay, and it's easy to prove that this is going to be the case. I can prove it for you. So you can have a look. Okay, so to prove this one, suppose A is invertible. Okay, so this is, let me prove it. Let me prove it for you. So I go from this direction. The direction is suppose T, okay, suppose T of A of X, which is A times X. Suppose this is one-to-one, is one-to-one. Now I want to prove that the A is going to be invertible. If this is going to be the case, you see in this case, if you consider the system of the equation, you see this system, the system AX equal to the B. okay, has a unique solution, has a unique solution, unique solution. Unique solution if you, because if you have two solutions, okay, this is going to be the case. You see, if you have two solutions, if a of x1 is equal to the, okay, a of xu, for example, is equal to the b, and a of v is equal to the b. So what does it mean? And this mean, okay, then t of u is equal to the a of u is equal to the b. T of v is equal to the a times v, which is equal to the b. So this means t of u is equal to the t of v. But t is invertible. So since the t is invertible, this means u is equal to the v. Okay? So if t of a is going to be 1 to 1, so this system of ax equal to the b has a unique solution. You know that if you get unique solution, this means a is invertible. Because you have the a inverse, you multiply both sides by a inverse, and you get x, okay? So in this case, this means, therefore, just for information, it's nice to know. Therefore, a is invertible. Okay, a is invertible because the solution would be x equal to the a inverse b. Okay, so this is when it's inverted. The other way around, that's going to be easier. What's the other way around? The other way around is suppose a is invertible. Now we want to prove that the t is 1 to 1. If it is going to be a invertible, and suppose that t of u is equal to the t of v. You want to prove that u is equal to v. This is the way you do it. So this would be au. This would be av. Since a invertible, multiply both sides by a inverse. A inverse au is equal to the a inverse av. And you know what does it mean? So this is going to be a inverse a times u, and this is going to be a inverse a times v. But this is just identity. And this is just identity. So that gives you the fact that the u is equal to the v. So ta is 1 to 1. You see, it's something obvious, but we have to prove it because in a minute we are going to find the inverse of the t. So just want to make sure that they are, okay, they are associated to each other. So if one of them, if t is invertible, you can find the a inverse. If a inverse exists, then you can find the t inverse. Okay, that's a conclusion that we are going to have. Okay, so now we give you the definition of the inverse of a, okay, this linear transformation. So the definition is, because we prove everything for you. So if you give me a linear operator, if you like, if t sub a from Rn to Rn must be an operator. You cannot define the inverse of a linear transformation in general. Okay, if this is going to be 1 to 1, is 1 to 1. If it's going to be 1 to 1, then t sub a is invertible. Is invertible. invertible, okay, invertible, uh, okay, and this is the definition of its inverse, okay. So what is going to be the inverse of the, if you want to find the inverse of the TA, is going to be simply the same as, okay, this is going to be an operator from Rn to Rm, that's defined by, this is it, T inverse of A. You see, it's the same as T of A inverse, okay. So what does it mean? This means that T inverse of A at X is the same as a T of A inverse at X, which is simply A inverse of X. So basically, this is what you expect. If you want to find the inverse of a, okay, inverse of a linear transformation at X, you just simplify, it's going to be just A inverse at X. So there is a one-to-one correspondence, if you like. There is a one-to-one correspondence between the inverse of a linear transformation, okay, inverse of a linear transformation, and the inverse of a matrix A. It's not surprising because we connect everything to each other. So your job, a linear transformation would be given. They ask you to prove it's invertible and find the inverse. What you are going to do, you find the corresponding matrix A. You find the inverse of the A. As soon as you find it, this is the formula for the inverse of the operator. If this A is not invertible, this means your operator is not also invertible. Okay, and you stop. So you better check it first. Okay, you can go for it and take a risk to find out, but it doesn't matter. You are not going to be able to find the inverse of the A. And decide which method are going to use for the inverse. Okay, we go with that inversion method that we talked about it before. Okay, so let's give one example. So these are just for you better understanding the connection to see it, but basically, you see, all these are possible because this observation that if you give me any transformation, I can change it to the matrix form. Okay, it's great argument. You can use it even for calculus 3. Okay, so this is it. We give you one on the test, on this quiz. Example, show that. Okay, show that the operator. Show that the operator T from R3 to R3, okay, where or defined by, this is the definition, T of x1 comma x2 comma x3 equal to, is equal to the x1 minus 2x2, okay, plus x3 comma x2 minus x3 comma 2x2 minus 3x3. Okay, we want to show that this is invertible. Is invertible. Okay, and find the formula. Okay, so if this is going to be defined, we can show that this is going to be invertible. Okay, it's going to be invertible and find a formula. A formula for its inverse. its inverse. That's it. So basically, this linear transformation is given to find the inverse. That's it. What is going to be the inverse of this one? Okay, so it's your job. You know that. Solution. You are going to find. You are going to work on the associate matrix. So find the matrix. We just remind you that. Recall that. If you want to find the A inverse, if you want to find the T inverse of A of X, it's the same as what? It's the same as T A inverse. Okay, I'll just write it down. It's A inverse times X. Okay, so the question is, what is A inverse? Okay, you find the A. That's it, 3 by 3 matrix. A is equal to, get the matrix. This is it. The first row would be 1, -2, 1. The second row, there is no x1, 0, 1, -1. The last row is going to be 0, 2, -3. Okay, so this is going to be your matrix, and work on this one and find the A inverse. That's it. Okay, you know how to find it. You have to write this one. This is going to be, I just used the inversion method. 1, -2, 1. And it's going to be 0, 1, and -1. And the 0, 2, -3. Remember, we put the identity matrix here. Identity matrix is going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, we start with this one and we change it. So this is going to be A. This is going to be identity. You have to work on this one, change this part into the A, so the other one would be A inverse. Okay, the row echelon form one. We already got the 1 here. Okay, and we got the 1 here. We have to change this one into the 0 because we already got the 1, and change this one into the 0 quickly. So I'm going to change this one R1 into the R2 plus 2R, R1 plus 2R2 to make this one 0. And this is going to be R3. I'm going to change this one into the R3 minus 2R2. Okay, if you do it, so what's going to be the conclusion? The conclusion is going to be, this is going to be 1. We get the 1, 0, 1, 0, -1. And the other side, we get the 1, 2, 0. R1 minus 2, R2. The second part is going to be the same. Okay, this is going to be the same. And the last one, R3 minus 2. Okay, this is it. That give you 0. That makes it to the 0. Okay, and this would be positive to -1. Okay, -1, and we get the 0, -2, and 1. R3 minus 2, R1. Okay, so this is it. So I have the 1, 0, 0. I have this one too. So I have to work on the second. To the third one, I make this one into the 0, 0, and I change the sign of the last one. Then we are done. Okay, to make this one into the 0, I take the R1 and I just check the R1 minus R3. So that make it into the 0. Then this is it. I have to change this one too. Okay, so I do two at the same time. So I change this sign. So that give me +1 that I'm going to be interested in. Okay, and in the middle one, I have to make this one into the 0. So what I do, this is the R2. I get the R2 minus R3. Okay, do these all operations together, and that give you quickly what you are interested in. So it's going to be 1, Okay, so if you do all these operations, this is the result: 1 0 0 0 1 0 0 0 1, and the other part we get 1 4 negative 1, and we get a 0 3 negative 1, and we get the 0 2 and negative 1. That's it. So this would be identity. So this would be A inverse. Okay. So since you can find that this is it, this means TA is invertible, and you have to find that formula. T inverse of A is going to be A inverse times X. Okay, you have to give us a formula, and that would be easy to find. Okay, you know that the A inverse is coming from here. You can do it right away, or just if you want a justification, this is it. The T inverse of A, okay, at that point, at X, if you like, is going to be equal to, this is going to be the first one. You see, this is X1. You can rewrite it or just do it right away. So the first one is going to be X1 plus 4X2 minus X3. That's the first component. The second component, there's no X1 and the X3, so that gives it 3X2. And the last one, there's no X1, so that gives you 2X2 minus X3. This is it. That give you the inverse. Quite nice method, you see. So we can take care of all the linear transformation because we're just working with the matrices. Okay, we work with the matrices, and this format, we talk about composition, and that give an idea really of whatever we can do with this type of ideas. That's it. This is all we need from that 4.10. Okay, we are not going to do anything else in this chapter. We are done with the chapter 4, and we are ready to give you the quiz at this time. Okay, so I post a practice quiz for you. Just leave it for a couple. I post it later today. Okay, then by Saturday, I just also, or maybe sooner, I post a solution for you, answer key. Okay, then I post the quiz number 2, and you should be able to do it by Monday as usual that we talk about. Okay, the number of the assignment. I may give you a couple of more days for the assignment. Maybe by Tuesday, I just check to see how many do we have, and then but we try to give you the quiz on Monday. Okay, so study these the sections that we did, and you should be fine. Okay. Then for the rest of the course, we get to chapter 5. Quite interesting one, quite interesting. It's not difficult, but that would be quite interesting for the application of the linear algebra. Okay, and we got enough time to do it. So that's it. I post this video quickly. Any question, let me know. Email me, and be prepared for the quiz. Okay, that's it. Have a good day. Take care. Bye bye.